Hey everybody, this is Cooper, and today we're going to be talking about neural nets. So let's start this off with a recap. So we started understanding that we can have multidimensional data. So we have right here that our x can go 1 through n when we have n pieces of data, and we can also have d dimensions. So now we're going to have multiple different inputs at a time. And we also saw that we can do the same for outputs. So now we can do the exact same notation, and of note again is that we have D and C respectively, and these do not need to be the same. So we can have 50 different inputs map to 3 different outputs. It doesn't matter what those numbers are, we can do it all the same. And we saw that that is essentially the same as any of the other regression we were doing, we just do it multiple times. So we have an updated definition of our models, or of our machine learning. So now we say that we are using data to tune the parameters of a model to minimize a loss function that measures how poorly it matches some function. So we defined a couple loss functions last time. We talked about MAE and MSE, which are the mean absolute error and mean squared error. Watch that again if you don't remember those. And now we understand that really what we're doing is we're minimizing that loss function. And it will get some function's behavior because we are minimizing that, but in reality, that's what we're going to be wanting to do. So we have a new updated diagram too. Here is what our new diagram of machine learning looks like. This is a very general way of putting it, and it's not. There are a lot of different models that could go here, but we're going to talk about very specific ones. I know it's a little bit cut off in the video, but there's just two Y's here. If you don't remember what it looks like, you can look at the last video too. So we're finally going to actually be able to apply this idea. I know we did a 2-to-1, but that wasn't so much doing this. We're going to do neural networks today, which will have multidimensional input and multidimensional output. And we're going to see how it all wraps together nicely. So this right here is going to be our new data set. So this is the data set that we are going to be working with. It's called MNIST, and it consists of 28 by 28 grayscale pixel images. So each of these pixels correspond to some number between 0 and 1, and they are 28 by 28 large. And each of them is one digit, 0 through 9. And we are going to classify them. And better yet, we're going to make a neural network do it. So this is going to be our data for our neural network. This is sort of considered the most basic vision data set that there is. It's very much the hello world of machine learning community. You will probably hear that said at some point along the line too, by more than just me, I guess. So let's talk about a very basic idea of what a neural network is. Let's look at a very small version of this. So we have 3 inputs here, all going to 1 output. So we have a 3-to-1 here. And each of these arrows here are going to correspond to 1 weight, or 1 parameter. So each of these are going to be 1 parameter. And what we do in this is we're going to say that the output of this is going to be the sum of each of the x's multiplied by their corresponding weight. This is essentially just the same as doing a matrix multiplication or a dot product in this case, and we can just take the output from there. So this very, very simple idea of what a neural network is actually called a perceptron, which was the very first iteration of, probably not the very first, but it was the early successful iteration of a neural network. So you'll probably hear this word said at some point, and it really is just a simple model like this. The reason that a model like this is chosen is that doing this sort of matrix multiplication makes taking the derivative very easy. As we'll see later, that is important to training a neural network. All right, so that doesn't seem to connect to our data set, doesn't seem to really be helpful for doing anything. It's a very simple case. So let's immediately make it more complicated. So now what we're going to have is we're going to have inputs, a whole layer of inputs. This is what we're going to be calling layers. And we are going to connect a weight from each of these inputs to each of the nodes in the next layer. I didn't draw them all because it is kind of a hassle to draw them all, but there is a connection from each of these to every single one of the rest of these. And that property where we have a single weight going from each of these to each of the nodes of the next layer in a neural network is what we call fully connected. So if you're a fully connected neural network, this is what we're talking about. And of course, there are many, many different arrows. There's an arrow going from here to all of these, and so on. So there are quite a few different parameters here. And likewise, on the next layer, we have the same behavior. We have a fully connected network here. So you can imagine all the weights going in here. And now we can sort of rationalize what the size of this needs to look like for the MNIST task. So as an input, we know that we have 28 by 28 grayscale images. That means that we will need 784 different inputs. Each of these nodes on our input is going to correspond to a single pixel from our input image. So we're going to input the entire image all at once, which with each of these corresponding to a pixel, and then it will go through the neural network, and then our output will have one label for each possible class. So we have 10 different classes in this case. We have 0 through 9, and we want to have each one of these correspond to one of those. You might be thinking, if you are ahead of me on this, that we could just have a single output and have it correspond to the label of the data. So if we put in an image of a 9, we could have a single node here that we would want to output a 9, and we just optimize it to do that. The problem with doing this is that by its nature, doing that is then saying that an 8 is close to a 9, or that a 1 is close to a 2, and that a 0 is very far from a 9. And that's not exactly how we want our neural network to learn. It might make more sense after we talk more about gradient descent and how we train one of these. But if we do that, we'll end up with properties that we don't want to see in our neural network. So instead, we are going to have them each be a label, a single label. So one important thing that I noted is I said how big this one is, I said how big this one is, but how about this right here, this internal layer of neurons? How come I haven't said how big it is? And the truth is, this is a hidden layer, and we don't necessarily know how big it is. We are going to pick it somewhat arbitrarily. We can just decide how large we want our hidden layer to be, and that is going to be how large it is. And the reason we would want to change that at all is the larger it is, right, the larger we make it, the more parameters it has. So you can think about when we are creating a series of weights going from the input to the hidden layer, we will have a number of parameters equal to the size of this times the size of this, because we have one connection going to each of them. So when we make this bigger, we'll end up with many more parameters, and having more parameters means that there are more possibilities of what our neural network could represent, what it could do as a function. So we have a larger search space of possible functions that it's performing. So that is why we might want to change this, but if we make it too large, then we're updating a lot of parameters, and that can take a long time. So we need to balance what we do here. All right? So let's try actually running it with the data that we have. So we're going to initialize each of these weights randomly to start with. That's the general way of doing it. So they're just going to be on a Gaussian distribution, just random. So when we input an image, right, let's input this 8. It will be fed through here, and we'll do each of the operations, each of the dot products going through the layers. You can even imagine at this point that we can actually do the dot product very quickly because we have just essentially a matrix of weights, but we'll save that for now. So we do our operations, and we end up with these scores. All right, and this one right here I labeled in purple because we are going to treat that as the score of the label that we actually have. So we'll say that in this case this is 8. So this one is the score that we have for 8, and these are the scores for all of the rest of them. What you'll notice is that we are treating them like probabilities. This is not something that you can really do. You'll see that they add up to 1, and that they are all between 0 and 1, and all of that, all those nice things. So we're treating these like probabilities because of a technique that we can use in neural networks. It's softmax, and then we're doing negative log loss. But for now, just sort of believe me that we are keeping them as probabilities because it makes it a lot easier for us to analyze what we expect from the network and what we're getting from the network. So this process of taking these as probabilities, the particular process I'm talking about, and then doing the regression to maximize the probability of the one we want to see is called logistic regression. A fun fact about that is that logistic regression is not actually regression. It's a classification process, but it is doing essentially regression on our values here. So it's essentially the same thing as what we're doing before, but it is called logistic regression and it's a classification task. So it's a bit of a weird case. This is all well and good. I know I'm getting ahead of myself a little bit. We'll wrap back around. All you need to know is that when we input an image, we will get these probability scores. All right, and we are going to use these probability scores to somehow improve the model. So let's talk first about what the loss is. So earlier we had very easily, we just subtracted and then squared. And very similarly, actually, we can do something like that. So our output is now something looking like this. And the question is, what do we want? What does our label look like in this case? So it's not a single number, even though we have single number labels. What we're going to do instead is we are going to convert it into a vector like this, where the label will have 100% probability and everything else will have 0 probability. It should be 100% likely that it's an 8 because it is an 8. And we're going to treat it like this. So then all we do is we do our subtraction, we do this, and we get our loss function. You'll notice that each of these are just equal to their magnitude except for this one, which is the one that we wanted to see 1 out of. All right, so this will actually become the loss. And you can think for yourself for a second what the mean absolute error from this loss would be. And the answer is that it would be all of these added up divided by 5. In reality, it's actually divided by 10 because we have 10 classes, but I sort of made it smaller so that it fit on all the slides. And we'd get 0.28 or 0.14, depending on how you're calculating it. So we have a loss function. We can get the loss off of our output. That's all well and good. The problem is we are now looking at a task where we can't exactly just find an optimal solution. Before, when we were doing regression, we could just, in closed form, calculate what the optimal parameters were, but we can't do that anymore. So we need to get a little bit creative. So we go back here, we can see our loss. You can see that we have that being different. And I have both here, the MAE and the MSE. Just want to point out that they are, in fact, slightly different. It doesn't come across that much in this case where we have very low values. When we have very big values, it's a lot more of a discrepancy between the two. All right. So now the question becomes, we have our loss function, we have our neural network. How do we update our neural network? How do we get a better neural network? How do we get the best neural network? The real answer is we can't get the best one. In most of these cases, there is not really a clear way to get the best one, but we can do something kind of clever. So we have this and we have our loss coming through. And what we want to do is we want to find the gradient of our loss. So the gradient of our loss, in like this very simple case right here, is the partial derivative of each of its parameters, every single one of its parameters, with respect to loss. So we're going to find every single one of those, and that will give us our gradient. If you don't remember what a gradient is, I'll give you a very simple refresher soon, but you also should probably try to remind yourself from 233 what it is, just so that this is a little bit more compelling. So we're taking the partial of all of the different parameters, and that is our gradient of loss, because it will inform how we update each of our parameters too. So a little bit refresher on what a gradient is and why this is useful. So imagine that we have some graph here. This is a graph where the y-axis is our loss, and the x and y-axis, or I guess the z is the loss, and the x and the y here are both just parameters. So this would be a model with 2 parameters, very simple model, but it is easy to visualize. And we can think that an initialization of our 2 parameters would correspond to some point on this surface. You have some point on the surface with some loss, so if we put in this and this into our model, we would get some amount of loss. We'd get 0.4 or whatever it is. Now, if we were to take the gradient of the loss function, that is exactly the same as finding this line right here, which is the direction of steepest ascent up the curve. So if we were to move in this direction, we would be heading up the curve of the loss function, ostensibly increasing loss. Now, this is not immediately helpful. I mean, we don't want to increase loss, we want to decrease loss, right? So that's not immediately helpful. But there is a nice property of gradients that we can abuse right here, and that some clever person was very happy to abuse early on, I assume. So what we can do is we can actually take the negative of the gradient. If we move in the exact opposite direction, mathematically what we know is that that is the direction of steepest descent. And not only that, like we know that it is the direction of steepest descent, that's very good, but we know that if we take a small enough step in this direction, I mean minuscule in most cases, but if we take a small enough step, a sufficiently small step, then we know we are guaranteed to reduce loss, I guess unless we're at an absolute minimum already, but then the gradient would be 0. So we are guaranteed to reduce loss, or at least keep it steady. So really, you can start to intuit what we want to do. We want to take the gradient of our loss function in terms of all of its parameters, and then if we were to move in this direction, that is akin to us changing these parameters in this way, and by doing that, we know mathematically that we will reduce the loss. And if we reduce the loss, then we are getting better at our task. That is the general idea of it, and that is how we can actually approach it. So this is very clever. This is very important to know. This is essentially what gradient descent is. We'll talk more about it, but this is a very important idea to machine learning. It is why it is so important, and it's why we use neural networks. So definitely remember this. All right, so we definitely want to do that. Let's try to figure out how to do that. So we get to talk about some of the buzzwords now, which is nice. We got backpropagation, gradient descent, lots of fun stuff. But what we want to look at is, let's just take a very small neural network now. Let's take a 3-node neural network, just input, hidden, output. All right, and what we want to do is we want to find what the derivative of our weight 1 is, with our loss with respect to weight 1 is, because that will be informing how we change this particular parameter. We need it for the gradient in a very general way, but in particular, this will tell us how to update this parameter. And what you might remember from Calc 3, and it's a nice little useful trick, is that we can actually take these derivatives and chain them together. So we can actually use the chain rule here. So because it's pretty easy to find the partial of this weight right here, this parameter, we can actually just find that first, because it's just a simple matrix multiplication. So it's a very easy parameter, a very easy derivative to find, and we can just multiply it by this this partial derivative too. And this is very nice. We can just cancel these out and we get our partial derivative just like we do in chain rule. So we can do this over the course of as many nodes as we want and combining as many different nodes as we want, and we can just find any of these that we'd like. And this process of using these different partial derivatives to calculate ones earlier in the sequence is called backpropagation. There is a little bit more to backpropagation than this. I want to, be honest with you. We also do want to keep track of these values as we calculate forward, but the main idea is that we are going to be able to multiply these together with chain rule and any other of our rules to combine them, and we can backpropagate it through the network and find every single one of our partial derivatives, and in doing that, find the gradient. All right. So now we get to talk about how we actually use the gradient, because it is easy enough to say we'll just move down the hill. We'll keep walking that direction, but we need to be a little bit more specific about it. So the naive way of approaching this, maybe not as naive, but a naive way of approaching it is stochastic gradient descent, or SGD, which is another big name in terms of how we actually got into neural networks working and all of machine learning blowing up as it has. So the algorithm for SGD is as follows. So we have any parameter, I call it WI, but any parameter, every parameter even, is equal to what its current value is minus learning rate, this is our learning rate, times the derivative. So we're subtracting the derivative ostensibly, but multiplying by our learning rate. What we can think of this learning rate as doing, and this is a hyperparameter that we set before we train anything, what we can think of it as doing is indicating what the size of the movement that we're doing towards the negative gradient is. So if we have a very small learning rate, we're taking very small steps. If we have a big learning rate, we're taking big steps. So if we have an infinitesimally small learning rate, we have a mathematical guarantee that we're improving loss as we go, but that's not always exactly what we want, and it's also very slow to train. We need to balance those different properties of our network, so this is something that we need to keep an eye on, and we need to decide individually and case by case. So let's observe how it actually behaves in a sort of an empirical setting. So if we have our loss function here, I have the darker being deeper or lower loss, then we can start at some beginning state here, let's say. That's our initialization of our loss, of our parameters given our loss. So when we actually go to do this, we'll see that basically what we do is we find the direction of our negative gradient, and we just take a step. And we do that over and over and over and over and over again. And what we end up seeing is that it starts looking a little bit clanky. We're going up and then down and then up and then down. It's lots of individual lines, and it doesn't really go directly towards the bottom in a lot of cases. This is sort of like a shallow pail. It would do something like this. So that's not ideal, and it takes a really long time to converge, especially if our learning rate is really low. It would take a long time to go. So we don't really want that. And there have been a lot of people trying to create better optimizers, and I will talk about one, only one of many that we could talk about right here, which is called momentum. And you probably have figured out in the time it has taken me to say momentum what it does, and you are exactly right. Momentum is going to keep track of the direction that it's moving and how much it has moved in that direction. So what we're going to do is we're actually going to keep another variable now that we call velocity. So velocity is going to be essentially the same as what we're doing up here, except it will have this parameter here, mu, that will decide how strongly we hold onto the velocity that we were currently moving in. So what happens here is our velocity will be updated based off of our new partial derivative, and we will point in that direction. But if velocity is pointing in a different direction, we will still have some sway towards still going in that direction. So we are more consistent in the direction we're moving. We don't change as rapidly like this. And the idea is to give it momentum so that it will stay going towards the center. So what we do next is we're going to update our weights, and we'll just update it like this. We just update every parameter with the parameter like itself plus our velocity. And you can see if you check how the math works out, it is essentially exactly the same as you'd expect. And now when we actually try it empirically, we can see that if we initialize here, we'll expect that it will curve towards it a lot more because now it has some sort of momentum. But we also do get a negative consequence of doing this. We'll see that it will actually overshoot the goal, and then it will have to loop back around because by the time it's moving here, it is strongly, steeply going this direction, and then it can't stop itself fast enough. So this is a trade-off between different properties. This will converge here faster, but it does behave in a non-optimal way, where SGD really does just kind of move towards the goal, just slower. So it is the case, as with a lot of things in machine learning, because it is a relatively new field, there is no real secret sauce to understanding which one of these is better in any situation. And in fact, there are situations where one is better and there are situations where the other is better, and that goes for any of the other optimization methods that we are interested in. So no matter what, it is not a definite answer like this is best optimizer, this is best optimizer. It's something that you're going to have to decide based on what your task is and depending on what your network is. So it's something that you should keep track of and you should sort of understand. In reality, you really just need to understand this equation right here, and you need to understand what gradient descent is. That is much more important than understanding the difference between these, but it is something that you should keep in mind. All right, so I've also included here a couple materials. 3 Blue 1 Brown has an excellent coverage of deep learning and backpropagation that I recommend all of you look at. There is also an MIT lecture series that is quite good. It's entirely on YouTube. It is much more material than this is, but this one is very visually pleasing and covers basically the same exact material that I covered, even with the same example. Yeah. And then there is also Fast AI, which is a course where you can do some hands-on coding and make some of these neural networks. So check these out if you're interested. They are very good, and I recommend them. All right. Hope that all was good. See you next time.